Dr. Seeger here, and today we're over here at my ever busier lab station, and we are going to be doing some lab demos about heat today. And our overall goals of these demos will be to understand what heat is, as well as what turbulence is, and the relationship between the two. And that demo is going to relate to the conservation of energy and the idea that all energy one day ends up as heat. The second demo is going to be to learn the relationship between heat and density. So as you heat up a material, what happens to its density? And then our third demo is going to involve convection and conduction in a pretty interesting ice cube experiment. So let's jump right into our first demo, which is going to be about turbulence and heat.
All right, so what we have here is just a tank of water, and at the top there is a bunch of tiny little droplets of oil, which are going to let us see how the water is moving. At the bottom of the tank you have a ruler just as a reference point to the relative speed of what's going on here. And what this is going to be able to show us is turbulence. And I'll show you what turbulence looks like. So I'm going to move this water in a very uniform manner using this card. It's just a little piece of cardboard. And what you're going to see is when I begin moving this, it's going to be very uniform. And that's just kinetic energy. Anytime you see something moving in the world, we just say it's kinetic energy. If there's a mass moving, that's kinetic energy. But what you're going to see is that over time, this energy is going to become more and more chaotic. So there's still going to be motion, but it's going to be kind of random swirling motion. And then if we watch long enough, there's not going to be any motion at all anymore. So let's watch this once and see what happens. So you can see at the shadow at the bottom, there's still a tiny bit of motion going on your far left side, but compared to what we started with, there's hardly any motion left in this tank, as indicated by the droplets on the surface. Still a tiny bit of vortex going over in the top left corner. All right, so let's think about this situation as it concerns the conservation of energy. I put energy into this system. It was moving. It was clearly moving. And now, after a few seconds, we see hardly any movement at all. So where did that energy go? So I'm going to do it again. And this time I want you to focus on the relative speed of the water, of these swirling motions of turbulence, as we first start, kind of in the middle and at the end. All right, I think I like this angle even better. And we're going to watch this process of kinetic energy and turbulence to kind of nothingness. We'll watch it once in full speed, and then I'll slow it down for you so that you can make some observations about it. So here we go. Here's full speed. That one was not bad.
All right, so I hope that the shadows and everything came out okay in that demo and that you could actually see what was happening, but I just kind of want to describe what I see when I do it. Basically, when we start, and I give the water a little shove, the first thing you notice is that the water, kind of responds and begins to move, and it's all moving in kind of a uniform direction. And we call that just simple kinetic energy. When you have a mass of something that is moving and it's all kind of moving in the same direction, that's simply kinetic energy.
There's a calculation in physics. It's pretty straightforward to calculate. You just take the mass and you multiply it by the velocity squared. But then as we watched this motion of water progress through the tank, what you noticed kind of in the middle, hopefully, was that it began kind of breaking down and looking more chaotic, and you might have noticed even some like whirlpools sort of forming here in all of these different directions, right? And this uniform mass of water moving in one direction began to kind of break down and kind of swirl, and that is what we call turbulence. And basically what turbulence is just kind of random kinetic energy. It's still moving, and it's still water. It has a mass. It's just kind of moving in random directions now, and so it's still kinetic energy. We would call this turbulent kinetic energy, and there's another calculation that you can use to make, to figure out what the kinetic energy is there, but it's random, it's no longer uniform. And then as we kind of watched further and further, these swirling motions kind of got slower and kind of smaller over time. So instead of these big swirling fast currents, you sort of got smaller ones. Maybe a couple of little big ones held on, but they were slower, and eventually you couldn't see any movement at all. It was all still moving. We just couldn't see the motion because it's happening at like the molecular level. And random chaotic motion at the molecular level is simply known as heat. And ultimately, this is why I really like doing this demo, is because you can actually, in the last lecture we talked about how all energy eventually becomes heat, but with fluid and with turbulence, you can actually just watch the process of kinetic energy becoming more random and chaotic and smaller until all you have left is heat. So the energy that I put in to this body of water, initially, it's all still there, but it's a tiny bit of heat, which is just chaotic, random motion of atoms and molecules.
All right, so for our next party trick here, we want to learn a little bit about heat and density. I think we all know that less dense things tend to float on top of more dense things. And so we are going to kind of test the idea that heat causes something to become less dense. So we have one container of hot water that has been dyed red, and that's pretty much boiling hot water. And on the other side here, we have a container of blue water that is ice cold. So pretty much as hot and as cold as water can be, that's what we've got. And we're going to pour it into this container at the same time, and let's see what happens. So go ahead, write down your prediction. What's going to happen when I pour red and blue water into this container? The red water is hot, the blue water is cold.
Alright, now for the moment of truth. I'm going to be pouring these on opposite sides, so let's see what happens here. And you should have a pretty good view of it there. this again where I don't horribly burn myself. Should have brought oven mitts today. Didn't realize I needed them. All right, take two. All right, that's pretty clear that, yes, there is some mixing, but the blue water clearly goes to the bottom and the red water clearly went to the top. And you can actually see now they're starting to kind of reach an equilibrium where the surface is red, the bottom is blue. Something else you might have noticed is that even though I poured the red water on the left side of the screen and the blue water, the cold water, on the right side of the screen, the cold water pushed underneath the warm water and pushed the warm water over to the right, and you can actually still see it kind of sloshing back and forth. That is essentially what's happening with ocean currents. If you have an area of the world where water is getting colder and one area of the world where water is warming up, the warm water is going to push to the surface and expand. The cold water is going to sink, and then they're going to kind of slosh around, and that is essentially what ocean currents are. All right, for our last demo here, we are going to do an experiment where I let an ice cube melt in each of these beakers of water. And these two beakers of water are the same temperature. The only difference is the beaker on your right is salt water. So I've added salt to it. So I'm going to put an ice cube in both of them. The ice cube is going to be dyed blue so we can kind of see what happens to it as it melts, and so we have a better visual of it melting. But let me ask you, what do you think is going to happen? Which one is going to melt faster, the ice cube in the fresh water or the ice cube in the salt water? And why do you think that? And here's the moment of truth. These two ice cubes are the same size. I'm going to set them in the water, and let's watch what happens. Kind of position this one this way so we can see it. Both have a side profile now. Well, this is probably going to take a while, so let's go ahead and speed up our footage. Well, that might have come to a shock to some of us. The freshwater ice cube has completely melted, and the saltwater ice cube has still not melted completely. There's still a tiny little bit left right here up at the top. Yep, right there. So, you should have written down some of your observations here, but the obvious one is that the freshwater container is now completely blue, whereas the saltwater container, all of the blue dye, which was the cold water, is all kind of stuck at the top. It did not circulate around the container. So, why do we think this happened? Why did this freshwater melt so much faster than the saltwater? And I'll give you a clue. It has something to do with density. Let me ask you this. Which one of these two
types of water is more dense? Do you think fresh water or salt water is more dense? So when you add salt to water, do you think it gets heavier? All right, so now if we're talking about our explanation, it has to do with density and the idea that salt water is heavier than fresh water. So why do you think this happened?
All right, let's debrief a little bit here about what we just saw. So the fresh water was the winner, hands down. I know when I first did this experiment, I thought salt would win. After all, don't you put like salt on roads to melt ice? You would think it would work hands down. The reason for the freshwater winning has to do with convection. And some of the things you might have noticed during the experiment was that with the freshwater, and you might have even been able to see this on the camera, as the ice melted, you could kind of see that the blue dye, the cold water, was kind of moving to the bottom, and eventually the entire container kind of became blue as it was mixing together. Whereas the saltwater container, you could tell all the blue dye was concentrated at the top. And I just asked you whether or not you think adding salt to water would make it heavier, and I would assume that most of you thought it would. And yet, salt water is more dense than fresh water, and it's also more dense than cold fresh water. The ice cubes here were fresh water. They were not salt water when they froze. So what this means is that as this ice cube melted in the fresh water, the coldest water coming off of this ice cube could sink to the bottom, whereas with the salt water, the cold water could not sink to the bottom. So basically, as it tried to push down to the bottom, it couldn't, because the salt water was heavier than the cold water. And so all the cold water had to stay at the top, near the ice cube. You might already be kind of putting together what happened now. In the fresh water, the cold water could move to the bottom, which means whatever the warmest water in this container was would be constantly pushed up to the top. That is called convection. Convection was happening in the freshwater container. Coldest water was pushing to the bottom, the warmest water was pushing to the top. If the warmest water was constantly pushing to the top, the ice cube could constantly melt faster and faster. With the salt water, what happened is we did not have convection. All we had was only conduction, where the cold ice cube was in contact with warmer water, so there was a surface contact there, so it did melt. There was a heat exchange, but it was a much slower process. Convection is much more efficient at moving heat around than just conduction. So I hope that kind of helps summarize and reinforce these definitions for you, conduction and convection. Convection is where you have density, and the density of cold water pushing to the bottom and warm water pushing to the surface creates circulation and is much more efficient at moving heat than just conduction, where you have contact between a warm and a cold substance. All right, so let's just kind of wrap up everything that we learned today in our heat demos. Our first demo had to do with turbulence, where we watched kinetic energy transform, become turbulence, which was still kinetic energy. You could see it moving, and then eventually, just as the turbulence got smaller and smaller, basically turbulence at the molecular level, at the atomic level of atoms and molecules, is just heat. And so you could just watch the process, kinetic energy turning into heat, and this is what's happening all the time, everywhere, pretty much. In our second demo, we did conclude that hot water will push to the top and cold water will push to the bottom if they're mixed together. And this is pretty much the main driver of all ocean currents in the world. And in our last demo, we applied that convection and conduction have various effects on the world, but convection is very efficient at moving heat around, as indicated by the fresh water being able to melt the ice cube faster because the cold water could sink, warm water could come back to the surface and cause more and more melting.